Good morning and welcome to today's DIH Talk. My name is Santiago Uribe Diaz. I'm a digital advisor here at Lux Innovation. For those of you who are new to these webinars, there is a discussion window where you can put general comments during the session. And there is also a questions window in the middle where we encourage you to put all your questions during the session. At the end of this talk, there will be a Q&A session where we will review and the speaker will answer all these questions gladly. So today's topic is From Data to Digital Twins, Bridging AI and Process Understanding. So digital twins are visual representations of objects. There are more and more being used in the factories and in the industry world, because you can see what's going on with the real data of the factory in these representations. And today's presentation focus will be in understanding how data and AI can give even more impact to these technologies and make you better understand the processes of factories. Now, let me introduce you to the services of the DIH. So these services are 100% financed by the European Union and Luxembourg. No invoices, no administrative procedures. And our aim is to digitalize the companies in Luxembourg. We do it in different ways. So we have what we call assessments. The assessments are questionnaires that you can fill to find out your digital level. And depending on your answers, you will see if you should focus your energy and your money on AI, on data, on cybersecurity, on different directions. We also have a cybersecurity part. So here we work very closely with the Luxembourg House of Cybersecurity. They also have assessments completely dedicated to the cybersecurity topic. You can find out how good or how bad is the cybersecurity in your company and what actions you should take. And they have a very interesting program called the Room 42. So this Room 42 is a room in the Luxembourg House of Cybersecurity, and you can simulate a real cybersecurity attack with them, with your team from your company, with your real data. So this is an excellent opportunity to train yourself on how you should react on a real attack. Then we have the skills and trainings. So we work with the University of Luxembourg, and you can analyze together what are the topics that are most relevant to your company and to your employees, and together do a roadmap for trainings so that you make sure that you will address the most important skills in your company. Then we have technology tests. So here we work closely with the LIST, the Luxembourg Institute of Science and Technology. They regularly do workshops in which you can assist to their installations, and they explain different technologies in a very interactive way. So you will have a PC where you can test what the instructor is presenting you and learn to use these technologies. They also have the Test Before Invest programs. So this is even more personalized. Let's imagine you have plans of purchasing a technology like an ERP system. You can reach out to the LIST and do a test before invest. So you go to their installations again, and you can test these technologies with their help, with your real data on a session. And then you will find out if it's really worth it or not to invest in that technology. And finally, we have awareness on funding. So these are also webinars, but they are focused on the aids, the financial aids that the Luxembourgish government can give to SMEs on Luxembourg. Okay. And now, before introducing you to today's speaker, I want to ask you for your help. We are trying to find out what is the preferred language for these sessions. So in the future, would you like to have one session in English as we're doing today? Or would you prefer to have two sessions in German and French? If you want to vote, it's super easy. You just need to scan the QR code that you're seeing on the screen and answer that single question. So I leave this 5 seconds so that you guys can vote. Okay. So now, please join me on welcoming today's speaker, Eleni Koronaki from the Luxembourg Institute of Science and Technology. Welcome, Eleni.
Welcome. Welcome, everybody.
Okay, so I leave you the floor, Eleni. Let me see the presentations. Okay. Okay, the stage is yours.
Thank you, Santiago, very much, and welcome, everyone. Thank you for joining. I'm Eleni Koronaki. I'm a senior scientist in the Luxembourg Institute of Science and Technology, and today I will present digital twins focusing on industrial applications, not as a buzzword, but as a business tool for better decisions in manufacturing specifically. I will focus on three questions mainly. First, where digital twins create value today. Second, what trends matter now in 2026? And third, how an industrial team can start without launching a huge transformation program. I will use examples from automotive, electronics, and process industries because, in principle, the underlying logic is the same. Connect the physical process, the operational data, and model that helps people decide faster and with less risk. Over the past decade, digital twins have interesting concept discussed in research and engineering circles into a practical operational tool for manufacturing companies. Several pressures are converging in the manufacturing sector that make digital twins particularly valuable today. Manufacturers are expected to deliver more flexibility, higher quality, and lower environmental impact, often at the same time. And they need to do this while facing increasing complexity in production systems. One of the biggest challenges in manufacturing is unplanned downtime. In discrete manufacturing industry, studies estimate that between 8 and 13% of plant production time is lost during downtime. When we translate this across the entire manufacturing sector, the economic impact becomes enormous. In the US alone, downtime in discrete manufacturing is estimated to cause around $245 billion in losses every year. This includes lost production, delayed deliveries, emergency maintenance, and quality losses. And so these numbers illustrate why companies are increasingly looking for ways to anticipate problems earlier and manage operations more intelligently. For example, instead of waiting for a problem to appear on the production line, a digital twin can help predict when equipment performance is degrading, how a change in operating conditions will affect quality, or whether a production schedule will create bottlenecks. In fact, studies suggest that if digital twins were widely adopted across manufacturing, the potential annual benefit would reach tens of billions of dollars. These benefits would come from improvements in uptime, production planning, energy efficiency, and quality control. Several broader trends are accelerating the adoption of digital twins. Manufacturers are producing more product variants than ever before. Production systems must handle frequent changeovers and customization, of course. This increases the complexity of planning and scheduling operations. Digital twins help engineers test different production scenarios virtually, reducing the risk of disruptions. Another important factor is the growing shortage of skilled labor in many industrial sectors. So experienced operators and engineers are retiring while production systems are becoming more complex. In this sense, digital twins can capture process knowledge and operational insights in a digital form. This then helps organizations support less experienced staff with decision support tools and predictive analytics. Finally, manufacturers are under increasing pressure to reduce energy consumption and environmental impact. Energy prices have become and are constantly becoming volatile, And regulatory frameworks are pushing companies to track carbon emissions and resource efficiency. This is very critical today. Digital twins allow companies to evaluate how different operating strategies affect topics such as energy consumption, emissions, and material usage. This makes them a valuable tool. Digital twins are a valuable tool for balancing productivity and sustainability goals. Taken together, these pressures explain why digital twins are moving from a conceptual technology to an operational necessity. They're increasingly becoming a decision support layer that sits alongside the physical production system. So now, instead of relying only on historical reports or static simulations, companies can use digital twins to evaluate decisions in a continuous and proactive manner. In the next slide, we will look at what a digital twin actually consists of and how these systems are structured in practice. When people first hear the term digital twin, they often think of a 3D visualization of a factory or a machine. But a digital twin is much more than a visual model. A more accurate way to think about it is as a living decision model of a physical system. It is living because it continuously receives data from the real system and updates its state. And it is a decision model because its purpose is not only to observe what is happening, but to help predict, compare scenarios, and guide actions. A useful way to understand a digital twin is to break it down into 5 components, which you see in this slide. At the foundation, we have the physical system. This could be either a single machine or a robotic cell, an entire production line, or even a full manufacturing facility. In process industries, it might be, for example, a reactor, a furnace, or a mixing system. The digital twin always corresponds to a specific physical asset. It is not a generic model. The idea is that the digital twin becomes a digital counterpart of that real system. The second component is data, and this includes, of course, sensor measurements, process parameters, production history, maintenance records, quality measurements, and sometimes even contextual information like work orders or recipes. Modern factories generate big amounts of data through industrial IoT systems and manufacturing execution systems. But raw data alone does not create a digital twin. What matters is that the data provides a continuously updated picture of the system's current state. This is what allows the twin to stay synchronized with reality. The third component is the model layer, and this is where the digital twin becomes truly powerful. The models can include different types of representations. For example, physics-based models such as thermodynamics, fluid dynamics, or reaction kinetics. Another option is simulation models such as discrete event simulations of production lines, or analytical models such as statistical relationships and machine learning models trained from historical data. In many practical digital twins, we actually combine these approaches. For example, physics models may describe the process structure, while machine learning models capture patterns in historical data. And it is this combination that allows the twin to predict how the system will behave under different conditions. The fourth component is the decision layer. This is where the twin moves from being a monolithic tool to being a decision support system. Once the twin integrates models and real-time data, it can answer questions such as what is likely to happen in the next hour or next production batch? What is the root cause of a deviation we are observing? What would happen if we change this operating parameter? Which maintenance action would minimize downtime? In other words, this allows engineers and operators to test scenarios virtually before applying them in the real system. The final step is action. The insights generated by the digital twin can lead to actions, for example, adjusting machine set points, scheduling maintenance, optimizing production schedules, and others. In advanced implementations, some of these actions can even be automated through closed-loop control systems. But the key concept in digital twins is the closed-loop feedback that you see in the slide in the green dashed line. This means that the twin is continuously updated with new measurements from the physical system. If the system changes, for example, because of wear, environmental conditions, or process variations, the digital twin updates accordingly. This continuous calibration is what differentiates a digital twin from a static simulation model. Another important aspect is that a good digital twin does not exist only during production. It can span the entire life cycle of the asset. Some examples, during design, the twin helps engineers evaluate layouts and configurations. During commissioning, it helps validate production setups before even launching. During operations, it supports monitoring, optimization, and predictive maintenance. And during service and maintenance, it helps diagnose failures and improve reliability. All of this information is connected through what is often called the digital thread, linking data across engineering, operations, and maintenance. So I would say that the key takeaway is this. A digital twin is not just a simulation and not just a dashboard. It is a connected system that links physical assets, data streams, and predictive models to support better operational decisions. And when implemented correctly, it becomes a powerful platform for continuous improvement across the manufacturing lifecycle. When organizations begin exploring digital twins, the question is often, where should we start? In practice, the most successful projects do not start with a full factory model. They start with one decision that is expensive, frequent, and measurable. Digital twins create the most value when they improve a decision that already exists in the workflow, rather than adding something completely new. In manufacturing, we typically see three entry points. So the first place where twin software deliver value is before production begins, during engineering and planning. Here, the twin acts as a virtual environment where engineers can test decisions before implementing them physically. Some examples are testing production line layouts, validating robot paths, simulating machine interactions to, for example, detect collisions. In industries with complex equipment, such as the automotive, electronics, or process industry, this can dramatically reduce the number of physical trials required during launch. The result is shorter ramp-up times, fewer commissioning surprises, and safer startups. In some cases, companies report weeks saved during production planning simply because problems were identified virtually before even equipment was installed. The second major value area is during live operations. Once the twin is connected to production data, it becomes a decision support system for operators and engineers. For example, detecting early signals of equipment degradation, predicting when a machine is likely to fail, identifying the root cause of bottlenecks, comparing scheduling scenarios to maximize throughput. And instead of reacting to problems after they happen, teams can now anticipate the issues earlier and test possible responses virtually. This is very powerful, specifically for predictive maintenance, production scheduling, and investigating quality deviations. Even small improvements in these areas can translate into significant reductions in downtime and scrap. The third area where digital twins are rapidly gaining traction is sustainability and resource efficiency. Manufacturers are increasingly required to track and optimize energy consumption, water use, emissions, and of course, material waste. A digital twin can combine process data with models of energy and material flows to make these trade-offs visible. It can help, for example, answer questions such as what process settings minimize energy per unit produced or per batch, what combination of throughput and temperature reduces emissions, where is material waste introduced in the production chain, and others. This capability is becoming increasingly important as carbon reporting and energy costs become strategic issues for manufacturing companies. To make a pilot concrete, companies usually anchor it around one single measurable KPI. Typical starting metrics include planning or changeover time, first pass yields, downtime minutes, scrap rate, energy consumption per batch or per unit. The key is to pick one metric that the organization already tracks routinely, for example, on a weekly basis. That way, the value of the digital twin can be demonstrated almost immediately. And what is interesting today is that digital twins are no longer just engineering tools. They are evolving into operational systems that combine these aspects of simulation, real-time data, and AI to support daily decisions. And the latest trends regarding the uptake of digital twins in the industry demonstrate exactly that. So we will take a first look. If we look at how digital twins are evolving in industry, there is an important shift happening. In the early days, digital twins were often used mainly for visualization and offline simulation to help engineers design or for process understanding. Today, however, digital twins are increasingly becoming operational systems. They are moving from tools used occasionally by engineers to systems that support daily decisions in operations, maintenance, and planning. There are several technology trends that are driving this innovation now. The first major trend is the emergence of industrial AI co-pilots. These are AI assistants integrated directly into engineering and operational workflows. Instead of requiring engineers to manually search through dashboards or reports, the co-pilot can interpret data from machines, suggest even possible root causes of problems, and recommend operating adjustments, generate reports or diagnostics automatically. For example, an operator could ask, why did throughput drop in the last shift? And the systems could analyze historical patterns, sensor data, and process conditions to provide a diagnosis or a recommendation. These copilots are often built on top of digital twin architectures because the twin provides the structured representation of the system that the AI needs to reason about the process. The second important trend is the combination of physics-based models with artificial intelligence. Physics models are accurate but slow, while machine learning models are fast but require data and may lack interpretability. The emerging solution is hybrid modeling, where both approaches are combined. In practice, this might involve reduced order models derived from physical simulations, machine learning models trained on simulation data, physics-informed neural networks, or surrogate models that approximate complex simulations at a low cost. This hybrid approach allows companies to obtain predictions that are both credible and computationally efficient, which is essential for real-time digital twins. A third trend is the increasing importance of interoperability standards. One of the biggest challenges in industrial digitalization is that data often sits in separate systems. For example, control systems, manufacturing execution systems, engineering software, enterprise systems, etc. To address this, new standards are emerging, and one important example is the Asset Administration Shell, often abbreviated as AAS. The idea behind it is to create a standardized digital representation of an industrial asset, including its data, models, and metadata. This allows, of course, the digital twins to exchange information across different software platforms and even across different companies. In other words, interoperability is becoming a key requirement for scaling digital twin ecosystems. Another important trend is the combination of edge computing and cloud computing. Traditionally, industrial data was either processed locally on machines or sent entirely onto the cloud. Today, many architectures combine both approaches. At the edge, close to the machines, we can run fast analytics and monitoring algorithms. This reduces latency and allows immediate operational responses. Meanwhile, the cloud can provide large-scale computing resources to train machine learning models, to run large simulations, or to aggregate data across multiple production lines or production sites. This hybrid architecture allows digital twins to operate both in real time locally and at scale globally. Finally, sustainability is becoming a major driver for digital twin adoption. Manufacturers are under increasing pressure to track and reduce energy consumption, carbon emissions, water use, material waste. Digital twins make these trade-offs visible. For example, a twin can simulate how different operating strategies can affect energy consumption or product yield in conjunction with emission. This allows companies to find operating points that balance productivity and sustainability goals. It has been reported in many cases that digital twins are becoming a key tool for meeting carbon reporting and energy efficiency targets. We can already see all these trends in action in leading industrial companies, which shows that digital twins are no longer experimental technologies. They are becoming core components of modern manufacturing systems. So after understanding these trends, the next question is, how do these ideas translate to specific industrial processes? And this is what we will explore in the next slide. Here I will illustrate how digital twins are actually used in large-scale manufacturing in two very good examples. One is BMW and the other one is Siemens. First, in BMW, which has industrialized what they call the virtual factory, which is essentially a digital twin environment of their global production network. Today, this platform spans digital twins of more than 30 production plants worldwide, where production planners simulate manufacturing operations before anything is implemented physically. The digital twin integrates multiple layers of information from building layouts, equipment and robot models, logistics flows, vehicle design data, and even simulations of manual work operations. All these are combined in a real-time simulation environment, which is built entirely on NVIDIA Omniverse. This enables planners to test factory layouts, robot trajectories, and logistics flows virtually. Let me give you a concrete example of this implementation, which concerns vehicle launch planning. When a new car model is introduced, engineers must verify that the vehicle can move through the entire production line without colliding with surrounding equipment. In the past, this required physical testing with real car bodies, manually moved through the line over several weekends when the factories were not producing. In some cases, they even had to empty paint shop dip tanks to do the testing. With a digital twin, BMW can now simulate the vehicle moving through the production line in a digital way using construction data of their plant layout and 3D scans of the factory. The system automatically detects possible collisions, and now what used to take almost 4 weeks of physical testing takes about 3 days in simulation. And this shift has several business consequences. They have reported production planning costs projected to drop by up to 30%. New vehicle models can be prepared virtually before launch. Factory changes can be tested without interrupting operations. And importantly, the reason why BMW is focusing on that is that they plan to virtually integrate more than 40 new vehicle models into production by 2027 before they even are deployed physically in plants. So the digital twin is not just visualization, it becomes a tool for risk reduction in their new product launches. Now let's look at another industry, Siemens, where they are applying digital twins in their own electronics manufacturing plants. I will focus on the example of the factory in Erlangen, where digital twins of production systems are used to simulate manufacturing operations and optimize processes before any change is even implemented. Siemens reports several measurable improvements from combining digital twins, AI analytics, and automation. Namely, they report 40% reduction in time to market for new products, 50% reduction in carbon footprint. This is attributed to optimized operations, 60% improvement in quality using AI-driven inspection and process control, and also 50% increase in productivity through digital lean manufacturing methods. What is important here is the integration of digital twins with AI and industrial data platforms. And Siemens is now extending this approach through the industrial co-pilot developed together with Microsoft, which helps engineers and operators interact with the manufacturing systems using natural language and AI assistance. So if we take a step back, both of these examples show the same pattern, that digital twins are not only simulation models. They can help in many areas, in production planning, new product introduction, quality optimization, sustainability performance. And this is why many manufacturers are now investing heavily in this capability. Now let's focus more on how this translates to process industries. In process industries, for example, chemicals, energy systems, materials processing, the architecture of a digital twin is slightly different. Here, the core challenge is that process behavior is governed by complex physics, fluid flow, heat transfer reactions, multi-phase phenomena, and transport processes. This is where model-based digital twins become particularly powerful. A useful way to think about the architecture is in 3 layers. At the bottom, we have the physical system itself, which includes, for example, a reactor or processing unit, the sensors that measure temperature, pressure, operating conditions in general, the recipes and control parameters, and the real behavior of the process under different operating conditions. This layer generates the data string that continuously updates the twin. In many process industries, however, the measurements we obtain are partial and noisy, and they do not directly reveal the internal state of the process. The second layer is the model layer. Here we combine first principle models, for example, computational fluid dynamics simulations or reaction kinetics models, data-driven models such as machine learning or statistical surrogates, or a combination of both. This hybrid approach is becoming increasingly important. High-fidelity simulations and detailed physical models can capture the physics accurately, but they are often too slow for real-time decisions. Machine learning models, on the other hand, can make fast predictions, but if used alone, they often lack physical credibility. The emerging solution now is to combine both to find the balance between accuracy and speed of prediction. The third layer is the decision layer. This is where the digital twin becomes useful for operations. The twin can be used to monitor the process in real time or detect deviations from expected behavior. It can be used also to test alternative operating scenarios and optimize process settings. It can also support scale-up or reproducibility across sites. In other words, the twin becomes a decision support system for engineers and operators. And in the next slide, I will focus on the particular, actually, I will skip that and I will go straight to a main question that companies are often faced with, which is where do we actually begin with digital twins? It is easy to imagine a very ambitious projects, for example, building a digital twin of an entire factory. But in practice, the most successful implementations begin with a small focused pilot. A useful rule of thumb is to start with one decision, one asset, and a single measurable KPI. This helps the project become manageable while allowing the organization to demonstrate value quickly. The timeline shown here illustrates a practical 3-month roadmap that many companies follow when launching their very first digital twin pilot. The initial phase focuses on clarifying the problem. Rather than starting with the technology, the goal is first to identify a specific operational decision that is costly or difficult today. Some examples may include predicting when a critical machine is likely to fail, identifying bottlenecks in production lines, or optimizing energy consumption in a reactor, reducing scrap, or improving first pass yield. Once the decision is defined, the team should establish a baseline KPI. KPI might be, for example, the downtime in minutes, scrap rate, changeover time between different products, energy consumption per batch, and having this baseline allows the team to later measure whether the digital twin actually improves performance. During this phase, the team also maps what data already exists. This is important because in many cases, companies discover that much of the required data is already available through, of course, their sensors and the systems that they have already in place, maintenance records or quality control databases. The key task here is to understand where the relevant data lives and how it can be accessed. The second phase focuses on building what we might call a minimum viable digital twin. The goal here is not to build the perfect model. Instead, the objective is to create the simplest model that can support the target decision. In this stage, the team typically connects a digital twin to live or historical data streams, builds a first version of the model, which could be a physics-based model, a statistical model, or machine learning predictor, and begins validating the model against real events from production process. For example, if the twin is designed to predict machine failures, the team would test whether the model can correctly identify patterns that preceded past failures. This validation step is essential because it builds trust among operators and engineers. The final stage is where the digital twin moves from a prototype to an operational pilot. At this point, the outputs of the twin should be integrated into the workflow of the people who actually take the decisions. Some examples may include operators receive alerts about potential anomalies. Engineers need to compare different scheduling scenarios. Maintenance teams that may receive early warnings about equipment degradation. During the pilot phase, the team compares decisions made with and without the digital twin, and this helps quantify the impact on the chosen KPI. If the results show measurable improvements, the next step is to define how the solution can scale. And this scaling typically might involve applying the same twin architecture to similar machines, expanding from one production line to multiple lines, or integrating the twin with enterprise systems. It is important that the first project focuses on a KPI that is both measurable and meaningful for operations. And as I mentioned before, there is a great variety of such metrics that can be engaged in the beginning, notably planning time, changeover time, scrap rates, etc. It is important to note that these metrics are usually already tracked by operations, by operating teams, which makes the task to demonstrate the improvement much more readily available. The key takeaway, of course, is that successful digital twin projects do not start with massive infrastructure investments. They start with a small, focused pilot that delivers measurable value within a few months. Once the value is demonstrated, the organization can expand the approach step by step across the production system. At this point, it might sound like digital twins are simply a matter of building the right technology, but in practice, most digital twin initiatives do not fail because of algorithms or computing power or models. They fail because of how the project is framed, organized, and adopted inside the company. Across many industrial implementations, we see a few recurring pitfalls. Understanding this early can make a huge difference in whether a project succeeds or stalls. A very common mistake is to start with the goal of building a perfect digital replica of the entire system. Teams may try to develop a detailed 3D model of the plant, a very high fidelity simulation, or a fully integrated digital platform. The problem is that this can take months or even years before any value is even delivered. A better approach is to start with a specific operational decision, such as predicting machine failure, reducing change over time, etc. Once the decision is defined, the team can build only the level of model fidelity required to support that particular decision. In other words, the goal is not to simulate everything, it is to improve a specific decision. Another common issue is assuming that the challenge is simply collecting more data. In reality, many factories already generate enough quantity of data. The real challenge is data context. For example, sensor values only become meaningful when we know which machine they correspond to, which production order was running, which recipe or configuration was active, and when exactly the measurement occurred. Without the context, the data becomes difficult to interpret, and models may produce unreliable results. In practice, projects often spend significant effort building a clean data pipeline and consistent identifiers for assets, processes, and even events. This step is less visible than building models, but is essential for a reliable digital twin. Another major barrier is organizational. Digital twin projects typically sit at the intersection of operational technology and information technology. Operational technology includes the systems that run the factory, such as PLCs, SCADAs, process control systems, whereas information technology includes data platforms, cloud infrastructure, or enterprise software. If these groups work independently, the project can easily stall because the technical integration and ownership is unclear. Successful digital twin initiatives usually designate a single shared owner across engineering, operations, and digital teams. This ensures that the twin is aligned with actual operational needs and not just technical experimentation. A final pitfall is the absence of a continuous validation loop. A digital twin should not be treated as a static model that is built once and then deployed. Processes evolve over time, machines wear, materials vary, operating conditions change. Without regular validation against the real measurements and operational feedback, the twin can gradually drift away from reality. Successful twins include a process for continuous calibration, where models are periodically updated based on new observation. And this is what keeps the twin aligned with the real system. If we look at projects that succeeded, they tend to follow a similar pattern. They begin, even in the big companies that we explored before, with a small pilot project, with a clear business KPI and a specific decision that they need to improve. Then they build a minimum viable digital twin, and then they try to scale across machine lines or plants. This incremental approach allows companies to move from proof of concept to operational impact much faster. So the key lesson here is that digital twins are not only about technology, they're about aligning models, data, and organizational workflows around the specific operational objective. When the alignment exists, digital twins can scale rapidly. And when it does not, even the most sophisticated models may struggle to deliver value. I will close with one question that I think is the right starting point for any organization. Which decision in your operation would be worth simulating before you touch the line? That question is powerful because it avoids a technology-first discussion. It focuses the team on a real operational choice, like a launch decision or a maintenance decision, or a schedule change, etc. The references in this slide are all public and meant for follow-up. NIST provides a strong grounding for what digital twins are and how to think about value. BMW and Siemens provide concrete adoption signals. You can read all about it in their press releases. And the IDTA shows where interoperability is heading. Also, I included some sustainability references that show why digital twins increasingly matter beyond productivity alone. With this, I conclude my presentation and thank you for your attention. I don't know, Santiago, if we can go through some of the comments.
Sure. Thank you, Lenny, for this interesting presentation. So let's open the Q&A. Yes. So the first question is from Jibril. Jibril says, on ROA and limitations, in cases where value did not materialize as expected, what was the main blocking factor? Data quality, human adoption, or integration with legacy systems?
So that's a very good question. We touched upon this briefly during the talk. There is no one specific reason why digital twin adoption fails. It is something that is very particular to each implementation. But some of the most common reasons is not starting from the actual problem that will then lead to assembling the correct components for the digital twin. For example, does it really make sense to develop a very high fidelity 3D model of the process when you are lacking important information? You are much better off developing a very coarse model, a quick and dirty model to gain early insights. So I think the underlying principle is any type of failure starts from the issue, the actual engineering problem that we try to solve, and then assembling the appropriate components and not the other way around.
Thank you, Lenny. Thank you so much. The second question is also from Jibril. Regarding data maturity, to achieve these KPIs, first pass yield, downtime minutes, etc., what level of quality and granularity of historical data is truly necessary before starting a digital twin project?
So again, this depends on your goal. Do you want to extract some coarse-grained, top-level conclusions about your process? Do you want to include this interaction between the live system and your model? It all depends on what question you're trying to answer. And then another topic, which I also discussed about during the presentation, is how accessible the data is. We often see that organizations have the necessary data for what they want, the decision that they want to pursue, but it is split in different locations. It is not consolidated, and it is sometimes not very easily accessible. So I would say it is not only about data quality and quantity, but also about accessibility.
Thank you, Lenny. And we have a new question from Fateme. How to deal with latency sensitive applications near real time? Can DT be a good solution for these types of services?
So this is an excellent question stemming from the current concerns for, risk related to sensitive data. This is why one of the trends is combining localized edge computing with cloud operations. So many companies now select to build their digital twins close to their machine, so the data doesn't travel, doesn't move up to the cloud, with edge capabilities, which are now becoming more and more powerful and more relevant. And they try to do more top level modeling offline on the cloud. So yes, this is an important trend, and now we have tools to deal with this issue close to the machines without jeopardizing the security of the data.
Thank you, Lenny. So these were all the questions of this session. So thank you everyone for participating on this session. And thank you again, Eleni, for all these interesting insights of this rich topic of digital twins. And I leave this
Thank you.
QR. Sorry.
Thank you to everyone for participating and the interesting questions.
Thank you, Lenny. So with this QR, feel free to scan it and you have access to the program of our next webinars and all the activities of the DIH. Thank you and have a nice day.